Hello to everyone and welcome to day 13 of the Jamb Physics in 40 Days series. The Jamb Physics in 40 Days series is brought to you by Oyalen, where we believe that when you dedicate within 30 to 45 minutes of your time daily, you will be able to gather all the necessary skills and tools you need to ace Jamb Physics. So, peradventure, you are a student preparing for the Jamb exams, you want to take Jamb exams, and one of the subjects that you have selected amongst your subject combination is physics, then this video is definitely for you. So please do well to check out the videos that we have made from day 1 till today, which is day 13 of making videos in preparation for Jamb. So please check out from day 1 till now, because in each of those videos we not only give you a crash course of individual topics in the Jamb syllabus, we also solve multiple past questions on those topics, while we give you some tips that help you to solve those questions accurately every time you find anything like them. So please do well to check the videos, and also don't just enjoy it by yourself. Do well to share it amongst your friends who are also preparing for the exams, so that we can all ace Jamb Physics. So share the video, like the videos, and don't forget to subscribe to the channel as well, because when you subscribe, you are helping us to be able to make more helpful content like this. So hit the subscribe button and also click the notification bell icon so that you get alerted when we put out the next content and you'll be able to check it out. All right, so day 13 is about thermal expansion. And thermal expansion is not only going to be looking at solids, we're going to look at expansion in solids, in fluids, and also the anomalous expansion of water, because this is what is expected of every Jamb candidate preparing for the exams. When you're going to answer questions from thermal expansion, it's going to cut across these highlighted subtopics. You must be able to understand what we mean by expansion in solids. And take note, when we are talking about expansion in solids, there is the linear expansivity, there is area expansivity, and then there is volume expansivity. So linear expansivity is denoted alpha, right? And it is given by L2 minus L1 over L1 into bracket theta 2 minus theta 1. Or you can just say change in temperature for this part here. So, and of course, from this equation rather, we can also rewrite it and say L2 equals L1 into bracket 1 plus alpha change in temperature. So these two equations work when you are dealing with linear expansivity. And linear expansivity is actually defined as the change in length per unit length per degree rise in temperature. So, and that's what leads to this equation that you see here. And when you go beyond the first dimension of length, we can go to the next dimension, which is that of area. Another name for area expansivity is the superficial expansivity. So in case you find a question where they use the word superficial expansivity, you should know that they are still talking about area expansivity. Now that is denoted with the symbol beta. Now beta is given as change in the area, so A2 minus A1, this should be A1, per area per degree rise in temperature. So let's call this delta theta, just for simplicity. Okay, so we can also rewrite this and then say the new area equals to the original area multiplied by 1 plus the area expansivity multiplied by change in temperature. And then the same thing applies for volume expansivity. And take note, another name for volume expansivity is cubic expansivity. But that one is denoted with the symbol gamma. And gamma would be V2 minus V1 over V1 into delta theta. Or we just write the same equation and say V2 equals V1 into 1 plus gamma delta theta. Now, another thing you should bear in mind as you're working with this is that there is a relationship that exists between these different expansivities that we have here. For example, you should be able to derive that beta is actually twice of alpha and gamma is thrice of alpha. So for example, if you're looking for the new volume of a solid and instead of them giving you the cubic expansivity, they then go on to give you the linear expansivity and you want to apply this formula. So at this point here, you can change it and then say V2 equals V1 into 1 plus 3 alpha delta theta, because gamma here is 3 alpha. So that's just what applies there. The same thing happens at this point where we have beta. You can replace it with 2 alpha. So that's the relationship between linear expansivity, area expansivity, and cubic expansivity. Now, when it comes to expansion in fluids, however, it's a bit different, as in fluids we are going to be considering the cubic expansivity also, but you must take note that fluids do not have their own shape, but they take the shape of the container that they are inside, right? So that's one of the things that actually affects our calculation when we are looking at expansion in fluids. Like for example, if you put water into the pot and you put it on heat. Now, what you observe is that as the water is expanding, the pot too will be expanding due to heat. And in fact, the pot will react first even before the water. So it will look as if the water level drops, then later it begins to increase gradually, right? So this is one of the things you have to put into consideration when working with expansion in fluids, which is why we say the cubic expansion for fluids is given as apparent expansivity plus, as this is the real cubic expansivity, plus the cubic expansivity. So this equation applies when we are working with expansion in fluids. And when you are talking about apparent cubic expansivity, for apparent, we are looking at the amount of fluid displaced over original volume. This would be the apparent cubic expansivity. And then finally, we have anomalous expansion of water. This is a behavior of water where while other substances expand as you apply heat to them and contract upon cooling. Water does the same thing too, except within the range of 0 to 4 degrees Celsius, where the trend changes. Like for example, if you are cooling water down from 100 degrees Celsius, it will begin to contract until it gets to 4 degrees Celsius. At that point, instead of contracting, to begin to expand again until you get to 0. So that is why the maximum density for liquid water is at the 4 degrees Celsius mark. And this is the reason why you see that liquids like water, they always are freeze from the surface to the interior. And that is why you see that the surface of lakes always freeze over during winter, while the water beneath it remain in liquid state. And if you check well, you see that the temperature of the liquid water beneath the ice is at 4 degrees Celsius, which is the temperature that is warm enough for aquatic life to survive the long winter. So you see, it's actually an advantage, and at the same time, it can cause some chaos when you're trying to do some calculations like that. So it's always important to bear it in mind that water behaves in a different way, or as it is said in physics, in an anomalous way. So these are the things that is expected of you as you're preparing for the exams. So let's put all of these into work as we solve some past questions on thermal expansion. This question says, the linear expansivity of brass is 2 times 10 to the power negative 5 degrees per degree Celsius. And the volume of a piece of brass is 10 cm cube at 0 degrees Celsius. So what will be the volume at 100 degrees Celsius? Now, when we consider what we have in this question here, we see that V1 is given as 10 cm cube, and we are asked to find V2. Okay, we're working with the volume here, but we're given linear expansivity. Linear expansivity is 2 times 10 raised to the power negative 5, right? Per degree Celsius. Now we have to find the cubic expansivity in this case, which is gamma. Now gamma will be thrice of alpha, so we have 3 multiplied by 2 times 10 raised to the power negative 5. And it's also in per degree Celsius. So this would give us 6 times 10 raised to the power negative 5 per degree Celsius. And if we want to put this in normal form, that would be 0.00006. So now, working with this, we can then find the value of V2 using the equation V2 equals V1 into 1 plus gamma change in temperature. So that means we have to also consider the change in temperature. So the change in temperature, since we are looking at 0 to 100, that will give us 100. So let's apply all this into this formula. So V2 therefore becomes V1, which is 10, into 1 plus, now we find this, which will be 0.00006 multiplied by 100. Now let's see what this would give us. V2 would then be 10 into 1 plus. Now when we multiply this, that will get rid of 2 zeros here. So we'll have 0.006 here. Now this would mean that we have V2 to be 10 multiplied by 1.006. And by the time you multiply this, V2 is going to be 10.06 cm cube. Now let's look at the options. That's in option A. So we're going to register option A as the answer. In what range of temperature is the expansion of water anomalous? Now the anomalous expansion of water is the unusual behavior of water when you are heating it or cooling it down. Every other substance expand as you heat it up and also contract when you are cooling them down. And the same thing applies to water, except for a particular range of temperature where it goes against this rule. That is, when you are cooling it down, by the time it gets to 4 degrees Celsius, where it's supposed to continue to contract, it will then start expanding again until it gets to 0 degrees Celsius. So you see that range of temperature is from 0 degrees Celsius to 4 degrees Celsius. Now in this case, everything is in degrees Celsius, so it's easy to pick our answer as option C. However, another way that this question could be set is when they put the answers in either Kelvin or degrees Fahrenheit. So in that case, you may need to convert 0 degrees Celsius and 4 degrees Celsius to the expected temperature scale that you are asked to pick from. And once you do that, you should be able to get the answer in that kind of scenario. But for this, the answer is option C. A copper rod 5 meters long, when heated through 20 degrees Celsius, expands by 1 millimeter. Now, if a second copper rod 2.5 meter long is heated through 5 degrees Celsius, by how much will it expand? Now, things we need to note from this question is that the two materials we are talking about are copper, so they should have the same linear expansivity. So all we have to do is find the linear expansivity with the information given for the first copper rod and then apply that to the second copper rod. That way we'll be able to get the expansion in the second copper rod. So let's start with the first copper rod. To get the linear expansivity, that will be change in length. That is L2 minus L1, which is what we are given here as 1 millimeter. Now, always convert to the SI units that we have to use. This is in meters, so we have to convert this to meter. So it will become 0.001. Now, we divide that by the original length, which will be 5. Then we multiply that by the change in temperature. So that's given as 20 degrees. So when we apply this, we're going to be having 0.00001. And this is in per Kelvin. Okay, so now that we have the linear expansivity in this case, we can then apply it to the second copper rod. Now take note, in the second copper rod we are trying to find the change in length, that is the expansion. So L2 minus L1, which is the change in length, will now become alpha L1 theta. So now let's apply this here. So the change in length, L2 minus L1, therefore becomes now alpha, which is the linear expansivity, 0.00001, multiplied now by the original length. From the question we have it as 2.5, multiplied by the change in temperature, which is 5. Now by the time you multiply this, remember we are still working in meters, so we should end up with 0.000125. And to bring this to millimeter, because the options are in millimeter, we have to multiply this by 1,000. Now that will give us 0.125 millimeters. So the correct option here is option D. A metal rod has a length of 100 centimeters at 200 degrees Celsius. At what temperature will its length be 99.4 centimeters if the linear expansivity of the material of the rod is 2 times 10 to the power negative 5 per degree Celsius? Now, this is a 2019 UTME question, and to solve this, we're going to apply this equation. So we're taking this equation from the fact that alpha is L2 minus L1 over L1 change in temperature, right? So since we need the new temperature, we're going to apply this change of temperature as the subject of the equation. So let's say that is theta 2 minus theta 1. And that would give us L2 minus L1 all over L1. Then alpha comes down this way. Now, we already know what theta 2 is. According to the question, that is 200. So 200 degrees Celsius minus theta 1 would be... Now, the reason why I'm using theta 1 in this case is because when you consider here, you see that the object itself has a longer length at the beginning and then a smaller length at the end. So it's telling you that it's supposed to contract. Okay, so that is why we're using theta 1 in this case as what we need to find. So if it were expanding, for example, I'll be needing theta 2 in that case. So please take note of whether the object you're solving for is expanding or contracting so that you know whether you're using theta 1 or theta 2. And it also applies to when you're using L1, L2, A1, A2, V1, V2 in all the equations for expansion. So yeah, the change in length is from 100 centimeters to 99.4, and that difference is going to give us 0.6. Now divided by the original length of 100, then we multiply this by what we have as alpha from the question, 2 times 10 to the power negative 5, that will be 0.00002. Now, when you apply this with your calculator, you see that 200 minus theta 1 is going to give you 300 here. Now, let's find theta 1. So, take negative theta 1 to the other side, it becomes positive. And then what we have here is 200. And then when 300 comes this way, it becomes negative. So, minus 300 here. So, theta 1 is going to give us minus 100. And we are measuring in degrees Celsius, so we apply that here. So, when we consider the options, we see that the answer is D. The thermal expansion of a solid is an advantage in... Now, when it comes to thermal expansion, sometimes it's at advantage, sometimes it gives you disadvantages. Now, I think I've seen a question like this where you are then asked to pick the case where it is at a disadvantage. So then you can then compare that kind of a question with this, so and then see which one, so that you can have a list of where it is at advantage and where it's at disadvantage. Now in this case, we want to pick the one where it is an advantage to this case. So the first option we are given is in the balance wheel of a watch. Now the balance wheel of a watch is a metal strip that is built to precision. If there's a slight change in the length of that balance wheel, it will cause the watch to lose time. So in this case, you see it is not at advantage, rather it's a disadvantage, because if you cause it to expand, then the timing of that watch will no longer be correct. So this is a disadvantage, not an advantage. Now, B, we have construction of steel rail lines. Now, during the construction of steel rail lines, you always have to factor thermal expansion into it. Otherwise, it will create a serious problem for the rail lines. Assuming these were the rail lines, for example, now, and the train is supposed to run over this, run on top of this rather. By the time it begins to expand, what you will observe is that this place will begin to bulge. You see that bulge there, and by the time the train passes this part, you see this little bump you see here can derail an entire train when you consider the kind of speed at which the train will run on top of this. So this thing can cause the train to derail. That's a huge accident. So that tells you this is also a disadvantage. So when they are building rail lines, they often leave gaps between the steel rail to accommodate thermal expansion. Now, in the case of option C, we have construction of large steel bridges. The same thing also apply in this case here. You always have to leave gap for expansion. Otherwise, thermal expansion can cause the entire bridge to collapse. So you wouldn't want that, because that is also a disadvantage. That leaves us with option D, which is in the fitting of tires to wheels. Now you see that tires on wheels are always tightly held together. So whenever you want to pop it off or put it back on, you always have to rely on thermal expansion to cause it to contract a little bit. That way it will be easier to remove the tires from the wheel, and also to return them back after pumping and so on. So this is at advantage. So we go with option D. In this question from 2016, we are to find the decrease in length of a wire. Now, the original length of the wire this time is 10 meters, and it is cooled from 50 degrees Celsius to 10 degrees Celsius. Now, in this case, you see that it is contracting again. So that means that if we are using the formula now, we have to apply L2 to be the original length in this case, because that formula works best when you are looking at expansion. This time we are looking at contraction, so it's coming from a more longer length to a shorter length. So most times we apply L1 for 0 degrees Celsius. So just take note of that. But in this case, this is what the solution will look like. So now we know that L2 is supposed to be L1 into 1 plus alpha theta, right? So let's find L1. L1 would therefore be L2 divided by 1 plus alpha theta. Now L2 is 10 divided by 1 plus. Now alpha is 3 times 10 to the power minus 5. We can write that as 0.00003 multiplied by the change in temperature, that is 40. Now, when you compute this, you will find that L1 would give you 9.988 meters approximately. So now the decrease in length would therefore be L2 minus L1, and that would give us 10 minus 9.988. And this would therefore be 0.012 in meters. And to bring this to standard form, we would have it as 1.2 times 10 raised to the power negative 2. So from the options, that is option C. In which of the following devices is the expansion of solid a disadvantage? Now, we have the simple pendulum, the fire alarm, the thermostat, and bimetallic thermometer. Now, with the simple pendulum, we have an object that is oscillating, right? And once there is a change in the length, it's going to affect quite a number of things, like the period changes, and at the same time, if the space provided for a simple pendulum will not accommodate that swinging action, then it could lead to damage or things like that. Like for example, the simple pendulum, the pendulum clock, for example, you see it is in a chamber like so, and then this begins to swing about like this. If expansion should occur, it will make this longer, which means by the time it swings, it's going to be hitting these barriers that we have here, and we wouldn't want that. So it will be a disadvantage in this case. Now, in fire alarm, there are automatic fire alarms that has metallic strips that expand rapidly with heat. So whenever there is a fire and this thing, metallic strips begins to expand, it will flip the switch and then alert the fire department that there is a possible fire going on. So in this case, you see it's at advantage because when the owner of the house, for example, isn't at home, the fire alarm will be able to sense excessive heat and then trigger the fire alarm to call the right authorities to come and arrest such fire accidents. So, and then in the case of the third one, we have a thermostat, which you will find, for example, in your cooking, your hot plates, in your electric iron as well. What you have there, it's a metal strips that expand upon heating. So when you switch it on, they begin to expand rapidly like that. As it is expanding, it gets to a particular temperature where it will then go and hit the switch. So if this were a switch now, then you begin to expand this. At some point, it will get to this switch and then trigger it off. So that is why when you are ironing, you are able to set the limit of temperature you want. For example, if you are ironing cotton or if you are ironing silk and so on like that, they have their different temperature range, which would make this thermostat to trigger the electric iron to go off so that you don't burn what you are ironing. And the same thing applies to the bimetallic thermometer, which actually depends on the expansion of the bimetallic strip to detect temperature differences. So you see that 2, 3, and 4 are at advantage, while 1 is the only one that is a disadvantage. So when we look at the options, we'll pick option C. Which of the following materials has an increase in resistance with temperature? Folks, if you're yet to be subscribed to the channel, I would like to implore you to please do so. It's only going to take a second of your time, and when you subscribe, you're helping us be able to make more helpful content like this. So hit the subscribe button and also click the notification bell icon so that you get alerted every time we put out a new content. Now, in this case, let's try to recall the conditions necessary for resistance, especially in conductors. Now, you know that the conditions are, we have length, then there is area, then there is nature of material, and then temperature. Now, these are conditions that affect resistance, but in metallic conductors. So if that's the case, we can easily pick our answer from here as option B, which is metals. Two metals, P and Q, of length L1 and L2 are heated through the same temperature differences. If the ratio of the linear expansivities is 2:3 and the ratio of the lengths is 3:4, what is the ratio of the increase in length of P and Q? So some things we should take note of from this question is that when we consider the metal P and metal Q, they are going to have the same temperature difference. So we are not working around temperature difference because theta 1 and theta 2 of P and Q are the same, right? But we are given the ratio of their original length. So when the original length for P is 3, original length for Q would be 4. And we are also given the ratio of their linear expansivities. So when linear expansivity for P is 2, linear expansivity for Q will be 3. And what we are looking for is the ratio of their increase in length. So what we have to work with is increase in length for P and increase in length for Q. So here's the solution. Now the increase in length for Q, let's call that delta L1. That would be the linear expansivity for P multiplied by the original length of P. So let's call that L naught for P, and then multiplied by the temperature difference. So since the temperature difference is the same, we are just going to use theta in this case. Now the same thing applies to the change in length for Q. So and since Q is L2, so change in length for L2 is going to be, now we're going to be having the linear expansivity for Q multiplied by the original length for Q multiplied by theta. So let's find the ratio. So delta L1 over delta L2 would then be, so now we're going to be having multiplied by L naught of P multiplied by theta all over alpha Q multiplied by L naught for Q multiplied by theta. So easily we see theta cancel theta. So applying these ratios that we have here, now remember linear expansivity is 2:3. That is, this will be taking 2 while this is taking 3. So what we will have here will be 2 times, now what we have here is 3. Now here we have 3:4. So this one will be 3, then this one will be 4. So 3 cancels 3. Now what we have is 2/4, which is the same thing as 1/2. So the ratio of the change in length is then 1:2. And that is in option C. This 2007 UTME question says, a blacksmith heated a metal whose cubic expansivity is 6.3 times 10 raised to the power -6 per Kelvin. Now the area expansivity is, so we have to find area expansivity. Now if you note, cubic expansivity is 3 times of linear expansivity. So it means that linear expansivity will become cubic expansivity divided by 3. But area expansivity beta is twice of alpha, which will therefore be 2 multiplied by alpha, which is what? Gamma divided by 3. So we'll apply this as 2/3 of gamma. Now gamma is the cubic expansivity, which is 6.3 times 10 raised to the power -6 per Kelvin. Now when we apply this, what do we have? 3 here 1, 3 here, this is 2.1. Now 2 times 2.1 will give us 4.2, and that will be times 10 raised to the power -6 per Kelvin. And that is what we see in option C. Which of the following statements is or are correct? So the first one says, when a liquid expands, its density falls. Let's test that. So during expansion, we know that density is supposed to be mass over volume. So if our mass remains constant and is expanding, which means the volume is increasing. So the more volume you have, the lesser the density is. So that means this is true. Secondly, here we have, when a mercury in glass thermometer is placed in a hot liquid, the mercury level first drops, then rises. This should be then rises. Okay, and this is also true because of what we call apparent expansion, right? Because the glass in which the mercury is, the bulb of the glass would expand first before mercury, which is why you see that the level will drop before the level of mercury will then begin to rise. And this affects all liquid because they do not have a shape of theirs and they depend on the shape of their container, which will also go through expansion. So that's why statement 2 is also correct. Now we are left with statement 3. Statement 3 says the apparent expansion of a liquid is greater than its real expansion. Now that is false because we know that real cubic expansion equals apparent cubic expansion plus the cubic expansion of the container. So in this case, you see that real comprised of apparent and the cubic expansion of the container. So that means real is greater than apparent. So this is false. So the correct answer in this case is 3 only. So that's option C. A brass rod is 2 meters long at a certain temperature. Now, what is the length for a temperature rise of 100 Kelvin? If the expansivity of brass is 18 times 10 raised to the power negative 6 per Kelvin. So in this case, we have to find the new length, L2. And L2 would give us L1 multiplied by 1 plus alpha change in temperature. So L2 therefore becomes, now L1 is 2. Now this will be 1 plus, now remember that alpha is given as 18 times 10 raised to the power minus 6. We can put that in normal form as 0.000018. Now multiply that by 100, which is the temperature rise that we are given in the question. So L2 therefore becomes 2 multiplied by 1 plus, this will give you 0.0018. So that is L2 is basically 2 multiplied by 1.0018, and this will give you 2.0036 meters. Now considering the options we have, that is option A. A rectangular metal block of volume 10 to the power of negative 6 meter cube at 273 Kelvin is heated to 573 Kelvin. Now, if its coefficient of linear expansion is 1.2 times 10 raised to the power minus 5 per Kelvin, the percentage change in its volume is, so first we need to find the change in volume. So to find change in volume, we need the cubic expansivity, not linear expansivity. And cubic expansivity is 3 times of linear expansivity. So that will be 3 multiplied by 1.2 times 10 raised to the power minus 5 per Kelvin. Now what we are going to have here is 3.6 times 10 raised to the power minus 5 per Kelvin. So now we can find the change in volume. Now the change in volume will be the initial volume, that's 10 raised to the power minus 6, multiplied by 1 plus, now cubic expansivity, which is 3.6 times 10 raised to the power minus 5, multiplied by the change in temperature. So since we're going from 273 to 573, you find the difference here, that will give you 300. Now when you compute this, you will now see that the percentage change in volume would be what we have here. So 10 to the power of negative 6 multiplied by 1 plus 3.6 times 10 raised to the power of negative 5 multiplied by 300. Then we'll close that. All divided by the original volume, 10 negative 6. And then we multiply this by 100 to bring it to percentage. And what you should get is 1.08% when you do all of this with the calculator. And of course, this is approximately 1.1%. So the correct option is B. The ratio of the linear expansivity of copper to that of iron is approximately 1.5. Now, a specimen of iron and a specimen of copper expands by the same amount per unit rise in temperature. So the ratio of their length would then be, so let's find the ratio of length of these two specimens. Let's start with copper. So according to the first statement here, we know that the ratio of their linear expansivity is 1.5 approximately. So what we are looking for now is the ratio of their length. This is what we need to find. So now, when we look at this equation from here, we can tell that from what we are given here, that they expand by the same amount. That means that change in length of copper is equals to change in length of iron, and the temperature range is the same as well. So change in temperature for copper equals change in temperature for iron as well. So from this, we can then go on to use change in length as the subject of formula in each case. Now, what that will imply is that the linear expansivity of copper multiplied by the original length of copper multiplied by the change in temperature, let's just use theta since it's the same, should equal the same case for iron. So that would be alpha I, L of I, and then theta. So we see that theta cancels theta. Now from here we can then say the ratio of their lengths, that is LC over Li, will then be, now I've brought this here, so it means that this will have to come down here. So we have here alpha I over alpha C. But what we have is the reciprocal in this case. So that means that LC over Li would then be the reciprocal of this. So 1 over 1.5. Now 1.5 can be written as 3 over 2. So we write 1 over 3 divided by 2, which implies that we have 2 over 3. So the ratio is therefore 0.666 and on like that. So it's approximately 0.67, and that is option E. Now you can practice more with questions you'll find on the Exam Phone app. We're going to drop the link to download the app in the description box of this video. Click the link, which will take you to either the Google Play Store or the Apple Store, depending on your device. And then you can download the Exam Phone app and have fun while you play solving questions on any subject of your choice. The app is created in such a way that it is very interactive and very fun. It is just like a game, and you move from level to level as you answer questions on different subjects. So please download the app and register, play. And most importantly, it's also an app that allows you to earn as you learn. So you can also take advantage of that and earn while you also solve more questions on your subject of choice. And also do not forget to subscribe to this channel so that we can continue to give you more helpful content like this. Hit the subscribe button and also click the notification bell icon so that you get notified when we put out the next content. Thank you for following the series. I'll see you in the next video.